So hello and welcome to the long-awaited lesson on Taylor polynomials. We will be deriving Taylor polynomials. We'll be using them to make approximations, and then a few other things as well here. This is 9.7 in the old textbook. So here's what the definition of a Taylor polynomial is. If the function f has n derivatives at x equals c, then the polynomial p sub n of x, which you can see there, we're going to break that down in a bit, is the nth degree Taylor polynomial of f, and it's centered at x equals c. So let's look at what we have. We can see that it's, get it? We can see that it is centered at x equals c because the polynomial itself, if I'm looking, I've got a constant term, and then I've got x minus c quantity squared, all the way up, right, with the et ceteras, all the way up to x minus c to the nth power. We say that this is centered at x equals c because if you're thinking about algebra 2 and the shift that would have been made to this polynomial, making those all factors of x minus c means the function has been shifted to the left or the right, depending on what c is. So the function has been shifted to c, and so that's why we would be centering that at x equals c. Notice then what the other components of this polynomial are. The first one is f of c itself. So we'll have a value for the function at the center, which is c. The next one, the next term, has f prime of c, the slope of f at c. The first two terms, if you take the first two terms on their own here, this is actually just the formula that we've used for local linearization, to use the tangent line to approximate a value near a known value of a function. So that would just be the linearization that we've done before. But if we continue to take terms, here we'll take the second derivative of f evaluated at c divided by 2 factorial. That's our new coefficient. That's our coefficient of x minus c quantity squared. And then it's going to build all the way up to the nth derivative, that's the n in parentheses here, that's the nth derivative of f evaluated at c divided by n factorial. That would be the coefficient of x minus c to the nth power. If the function has infinite derivatives at x equals c, then you can make an infinite polynomial. The infinite Taylor polynomial will actually match the function exactly at some radius of convergence. And the radius of convergence is a topic for another day for this, but just know that this is how to create the Taylor polynomial. A Maclaurin polynomial, which you will also see on your AP test, you'll see those words. A Maclaurin polynomial is just a special case of a Taylor polynomial that's centered at c equals 0. So it's just a fancy way of saying that the center is going to be x equals 0 if it says Maclaurin polynomial. So Taylor polynomials fit into the broader category of a power series. And a power series would be the sum from n equals 0 to infinity of some coefficient and then x minus c to the n. So power series are useful. They are powerful, in fact, shall we say, because you can use them to quickly evaluate functions that would be difficult to evaluate otherwise, among other uses. But that would be the common one, I think, for the most part, why they would have been derived there. So in this first example, it says, let's find the Maclaurin polynomial. That means it's Maclaurin, so that would be centered at x equals 0, of degree 4 for the function y equals cosine x. So we're going to start by taking the derivatives of cosine x and then substituting in the value at the center so that we can start building up our coefficients. Just to do it in a nice orderly fashion so we don't accidentally mess up something. So the first derivative, or the function itself, right, f of x would equal cosine x. The value at x equals c, well, it's a Maclaurin polynomial, so that means that c, the center, is 0. And so I can write the little line that means evaluated, and if I'm evaluating this at x equals 0, the cosine of 0 is 1. Then I'm going to take the first derivative. So the first derivative of cosine would be negative sine of x. The next derivative would be negative cosine x. The third derivative would be positive sine x. And if I'm finding a degree 4, that means that I'm going to have to get to the fourth derivative. You can write that with a little Roman numeral 4 up there, or you can write it with the number 4 in parentheses, so that it doesn't mean f of x to the fourth power, but it actually means the fourth derivative if you put the little 4 in parentheses. So the fourth derivative would be back to cosine x, the original function. Evaluated at x equals 0, we've already done that. It's going to equal 1 right there. But let's go ahead and evaluate the others at x equals 0. If you have it labeled here in your column, then you don't necessarily need to write those that say evaluated at x equals 0, although that is a nice way to show what you're doing. So the sine of 0 is 0. The cosine of 0 is 1, but this is negative of that, so that becomes negative 1. And again, then the sine of 0 is 0. So those are my derivatives. Then I'm going to start building the Taylor polynomial. So it's going to be f of 0 plus f prime of 0, which is the first derivative, so that's over 1 factorial, and then that's x minus c, which in this case is 0, to the first power. Then I'll have the second derivative evaluated at 0, 2 factorial on the bottom, and then x minus 0 squared, etc. Right? That's how we're building this up. And so I'm going to just start by filling the things in that I already know. So f of 0 is 1 from here. So it would be 1 plus f prime of 0 is 0. This was already on my table that becomes 0, which means that this term is 0, right? So I'm crossing it out along with the arrow that's saying that's 0. F double prime of 0 is negative 1, so this would be negative 1 over 2 factorial, which is 2, times x minus 0 squared. Then I would have the third derivative evaluated at 0, but that's 0, so that whole term is going to go away there. This one was not a 0 term. I was okay on that one. And then I'm going to get to the fourth derivative term. So the fourth derivative term would say the fourth derivative evaluated at c, which was 1 from here, divided by 4 factorial, which is 24, and then x minus 0 to the fourth power. The way that you can denote this, you can denote this as t sub 4 of x. We can use a capital T to say that that's a Taylor polynomial. And the 4 means that that would be the fourth degree Taylor polynomial. Now that's only 3 terms, so you've got to watch out because the questions will ask for either the first 4 non-zero terms or the fourth degree Taylor polynomial, or third or second or whatever, right? But so just be careful that you make sure that you're paying attention to, is it asking you for the degree of the polynomial that it wants or the number of terms? Here I only have 3 non-zero terms, but it's the fourth degree Taylor polynomial. So I would say t sub 4 of x equals 1 minus 1/2 x squared plus 1/24 x to the fourth. That means that that is an approximation for what cosine x is going to be close to. So cosine x would approximately equal 1 minus 1/2 x squared plus 1/24 x to the 4th. Watch the notation here, because if we want to say what cosine x does equal, we would have to say where cosine x would equal this, like where would it converge, which again, we're going to be talking about that another day. And for it to ever be equal, we would need, if we're using an equal sign there, then we would need an infinite series here, which means that we would write our approximation, but then we would take note that this is going to have to continue forever. So plus dot 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 if you're going to make it an equal sign and not an approximately equal sign. Those are different ways that you might see that notated. What pattern do you see here, and could you make a formula for the nth term of that series? So if you notice, we had gotten that cosine x, we said, or our Taylor polynomial anyways, we had gotten 1 and then minus 1/2 x squared, which was 2 factorial, right, on the bottom. And then we had gotten plus 1/4 factorial x to the 4th. If you wanted to take a guess at the next term, maybe you are guessing that the next term would be minus 1/6 factorial times x to the 6th power. You may have noticed that I'm only getting even exponents here, that all the odd exponents ended up with the derivatives of 0, and so those are going to go away. So I'm actually only getting even exponents on my polynomial. That actually makes a lot of good sense, because if you think about the cosine function is an even function, as in f of negative x equals f of positive x, and so it would make sense that it can't have any odd degree terms in its power series. Hopefully you find that interesting. I think that is very interesting. Then it says, let's make a formula for the nth term of the power series. So if we see that we want the nth term, well, the x's, all of the exponents of x are even. So I'm going to say that this is x to the 2n power. Now, technically, if that's true, then the 6th degree power would be the 3rd term, which means that the 1 would be the 0th term. And that's actually okay, because we can make our starting index 1, or we can make our starting index 0 if we were writing this in summation notation, really as we see fit, whichever is the best way or the easiest way to write it. So we're just going to stick with that 2n for the power there and not worry about that. Then what's the coefficient? Well, we're going to have 1 over, it's the same number, factorial. So that would be 2n quantity factorial on the bottom. And then the signs are alternating. So let's figure out what we need to make the signs alternate. We'd have -1, and we would either need to the n or the n plus 1. So let's think about it. When the exponent is 6, that would mean n here is 3. And we have a negative sign, so if I just put -1 to the n, -1 cubed is -1. So that will work just dandy in trying to get these correct terms. And so that we have now come up with a formula for the power series for cosine of x. Please feel proud of yourself there. Our next task, it says, is to compare this graph of y equals cosine x with its Taylor polynomial of various degrees. So you can do that on your calculator, or I'm going to pull up Desmos for you. So I've pulled up Desmos, and if you notice, I typed in y equals cosine x in the first function, and then in the second function, I've typed the sum of the formula that I made for the nth term. So you can see most of it there, but I might have to scroll a little bit here, so that you're getting the sum from n equals 0 to k, because we decided we would have to start with a 0th term there, of -1 to the n times 1 over 2n quantity factorial times x to the 2n power. So that's what we came up with. And if you do this on Desmos, it'll ask you if you want to make a slider for k, which is our top index, like how many terms of this would we like to see, so that's kind of convenient. So if we look then at what we have, we're trying to make the blue line approximate the red line, right? We're trying to make our polynomial approximate cosine. So as I look at k, and as k goes from 0 to 1, you can see that in the neighborhood of x equals 0, it gets significantly closer. If k is 2, that's our 4th degree polynomial that we came up with, was until we got to k equals 2. And then if k would equal 3, then that would be our 6th degree polynomial. You can see that the blue line, the blue curve is getting closer and closer to, for a longer period of time, the red curve of cosine. As this continues, here would be k equals 4, 5, 6, 7, 8, 9, 10, and for k equals 10, which actually gets us to the 20th degree polynomial, that when we're looking at the 20th degree Taylor polynomial, it matches cosine x pretty exactly all the way out until about x equals 8, looks like, from x equals negative 8 to 8. So that's a pretty big neighborhood where these match. Turns out that this is going to, for cosine, that this is going to converge for all real numbers x. And you may be sitting there thinking, how do we know where it converges? Well, that, my lovely students, that is the ratio test. And so, preview of coming attractions, but we will be using the ratio test to determine for what values of x this is going to converge. Okay, so moving right along to another example. Let's look at the Maclaurin polynomial of degree 6 for x squared times cosine x. Since x squared is a polynomial in and of itself, I don't need to do anything special for multiplying that by cosine x. If I already have a polynomial approximation for cosine x, I can simply multiply that approximation by x squared, which is a polynomial. So I would get, if cosine x is going to equal approximately 1 minus 1 over 2 factorial times x squared plus 1 over 4 factorial times x to the 4th power, then x squared times cosine x is going to approximately equal x squared times all of those terms. So that would be x squared minus 1 over 2 factorial x to the 4th plus 1 over 4 factorial x to the 6th power. And that would be my Maclaurin polynomial of degree 6 there. If I wanted the general term for that, I can just use the general term that I've already made because I don't want to redo that work. So that was negative 1 to the n, and then I had 1 over 2n quantity factorial, and then I had x to the 2n power. Well, now I'm going to have x to the 2n power, but I'm just raising that power by 2 because I would be multiplying it by x squared. So this would be the general term. On the AP test, a lot of times they'll ask for the first 3 non-zero terms as well as the general term, something like that. So that was a little bit of a continuation of the example we had just done. Let's look at one that's not centered at 0. So this is asking for the 3rd degree Taylor polynomial. We want to center that at c equals 8 for the function y equals cube root of x. So I'm going to start by finding derivatives up until the 3rd derivative, and then I'm going to evaluate those at x equals 8. So the function itself is x to the 1/3 power. So the first derivative would be 1/3 times x to the negative 2/3 power. The second derivative, just power rule, I would end up with negative 2/9 times x to the negative 5/3 power. And then the third derivative would be positive 10/27 times x to the negative 8/3 power. To evaluate these at x equals 8, we're not using calculator here, right? One of the benefits of a Taylor series is that you can calculate things and approximate them without a calculator. So we know that the cube root of 8 is 2. X to the negative 2/3 power, if you need to rewrite that to remind yourself that this is the same thing as 1 over 3 times x to the 2/3 power here. And I know that if I'm trying to find that at x equals 8, I would want to take the cube root first and then square that. So the cube root of 8 is 2, 2 squared is 4, 4 times 3 is 12, and so this would equal 1/12. For the next one, I would get, again, if I rewrite this, then that would be negative 2 over 9x to the 5/3 power. So the cube root of 8 is 2. 2 to the 5th power is 32. And so I would end up with negative 2 over 9 times 32, which is going to simplify to negative 1/144th, I believe. For the third derivative, again, you can feel free to rewrite this as 10 over 27 times x to the 8/3 power, and then go ahead and substitute in that we're looking at 8, so the cube root of 8 is 2. 2 to the 8th power is 256 times 27, and then so we would get 10 over 6,912, which is going to reduce to 5 over 3,456. And yes, I am using my calculator for that. So if you want to use a calculator just for those computations, you would be welcome to do that, I suppose. Try to do as many as possible without your calculator. So now that I have the derivatives, now we just need to also remember that we will be putting in the factorials in the denominator for the coefficients as well. So if we start our Taylor polynomial, we would start with f of c, so that's just 2, f of x evaluated at x equals 8. So my Taylor polynomial, and this is a third degree Taylor polynomial, would equal 2, and then plus the first derivative, which is 1/12, divided by 1 factorial, which is just 1, and then times x minus the center, which is 8 to the 1st power. For the next term, I'm going to have minus, because I see this negative 1/44th here, so that's going to be minus 1 over 144, but also a 2 factorial on the bottom, and then x minus 8 quantity squared. And then our last term, and then I'll go back and simplify part of this. So then our last term would then be plus 5 over 3,456 times 3 factorial, which would also be on the bottom there, and then x minus 8 quantity cubed. That would be our third degree Taylor polynomial. If we simplify this, just let's see where I have some room to do this. I'm going to try and get this all written right here. Then I would get that that would be equal to 2 plus 1/12 x minus 8. And then 144 times 2 would be the 288. So minus 1 over 288 x minus 8 quantity squared. And then plus 3,456 times 6 gives us 5 over 20,736 x minus 8 cubed. That would be our third degree Taylor polynomial. This may not look like a great polynomial for you, but it's so much easier to evaluate a polynomial than it is to evaluate a irrational expression like the cube root of 8.1, let's say, or to evaluate a sine or a cosine function, or to evaluate an exponential function. With simple tools, we can evaluate this polynomial. So if I want to use that polynomial to approximate the value of 8.1, which is pretty close to the center, right? So we need to see, sometimes some polynomials only will, or some Taylor series will only converge at the center, whereas others will converge farther away. And so we would use the ratio test to examine where these power series are going to converge. In this case, we're not doing that today, so we're just going to put in 8.1 for x. And when we do that, we get 2 plus 1/12 times 0.1 minus 1 over 288 times 0.01. 0.1 squared, right? 1/10 squared would be 1/100th. And then plus 5 over 20,736 times 0.1 cubed, which is 0.001. Computing that, let's see what we get. 2 plus 0.1 times 1/12 minus 1 over 288 times 1/100th plus 5 divided by 20,736 times 0.001. If I typed this into my calculator correctly, I'll give you a few decimal places. We get 2.008298852. That's all the decimal places that my calculator gives me. That makes sense that it's something a little bit more than 2, because we know that the cube root of 8 is 2. If we actually type in our calculator the cube root of 8.1, let's see what we get. We get the actual cube root of 8.1 is 2.008298885 is the decimal places that my calculator gives me. Look how close that Taylor polynomial is. I mean, that is close to really, really far out there. You should be very impressed with that. All right, so one more example. We're going to look at the function, the rational function, y equals 1 divided by x plus 1. And we're going to look for the 4th degree Maclaurin polynomial, which means it's centered at 0. So we're going to start by finding the derivatives. I'm going to go ahead and just write y as x plus 1 to the negative first power. So then y prime is going to equal negative 1 times x plus 1 to the negative second power times the derivative of x plus 1, which is just 1. So y double prime is going to equal 2 times x plus 1 to the negative third power. Y triple prime would equal negative 6 times x plus 1 to the negative fourth power. And the fourth derivative would equal positive 24 times x plus 1 to the negative fifth power. Then I'm going to rewrite these so that I can evaluate them at x equals 0 nice and easily, or not have to worry about thinking of that. So that would be 1 over x plus 1, negative 1 over x plus 1 quantity squared, 2 divided by x plus 1 quantity cubed. Remember, the 2 still is on top, right? It does not go with the negative exponent. The next one, I would have negative 6 times x plus 1 to the fourth power. If you can do this straight from the get-go and not write the other ones, then you are welcome to do that. And then this one, I would have positive 24 over x plus 1 to the fifth power. So then evaluated at x equals 0, if I put in 0 for these, I get, evaluated at x equals 0, I get 1 here. Similarly, evaluated at x equals 0, I get negative 1. Sorry about that. Evaluated at x equals 0, 2, evaluated at x equals 0, negative 6, and evaluated at x equals 0, 24. So then those are going to be part of the coefficients of the Taylor series. Of course, I have to divide by the factorials as well. So I'm going to start building these up, and I'm going to get, well, remember the center is 0, so this is just going to be x minus 0, so I'm not going to bother to write that this time. I would have the actual value of the function at 0, which is 1. And then the next one, which would be minus 1 over 1 factorial times x to the first power. Then I would have plus 2 over 2 factorial x squared. And then minus 6 over 3 factorial x cubed. And plus 24 over 4 factorial x to the fourth power. This would be my fourth degree Taylor polynomial of x, centered at x equals 0. If I simplify this, I get 1 minus x plus x squared, minus x cubed, plus x to the fourth. And I'm hoping that you recognize that we've actually done that before, interestingly enough. And so let's just recap that so that hopefully you're making some connections here. We did this as a geometric series a few sections ago where we said that this was 1 over 1 plus x, which was 1 over 1 minus negative x. And we equated this to the form a1 over 1 minus r, which is your infinite sum of a geometric series. So we said that must mean that the first term, a1, is 1, and that our common ratio, which is what we're multiplying by each time, is negative x. So doing that, I would start with 1, and I'd multiply by negative x, so I'd get minus x, and positive x squared, and negative x cubed, and positive x to the fourth, etc. And if you notice, that's the same thing that we got by taking derivatives and making a Taylor polynomial of it. So again, beauty in that there are multiple methods that seem to have nothing to do with each other, but you're getting the same polynomial, that the mathematics is consistent in and with itself. So because we've done this one geometrically, we know that this is going to converge when the absolute value of r is less than 1. So that would mean negative x absolute value has to be less than 1, which means that x has to be in between 1 and negative 1 for this to converge. And we could graph this one as well, and we could see that the more approximations that we take, the closer it's going to be, but only in the neighborhood between negative 1 and 1. So I hope you enjoyed the series premiere for Taylor series. And then we will be coming back at you with error, LaGrange error, and some approximations in just a day or two. Enjoy.